Hello, everyone. And our next speaker is Professor Raul Curto from the University of Iowa, who will speak on an operator-valued version of Potapov's matrix-valued factorization result.
Okay. First of all, I'd like to thank the organizers for giving us a wonderful semester of great topics and great talks, and in particularly to Professor Javad Masregi for the kind invitation to give a talk at this workshop on truncated Teplis operators. The work that I want to discuss is joint with In-Sung Wang from Sungkyun Kwang University in Suwon, Korea, and with Woo-Yeon Lee, who is at Seoul National University. We've been working on an operator value versions of different results that come as the conclusion of the Berling-Lax-Helmholtz theorem, or as consequences of that, and more recently on an extension to operator value of Potapov's matrix value factorization result. My talk today is based on primarily an article in Advances in Math in 2014, a memoir in 2019, and a journal functional analysis paper that was recently published. Now, we also have a recent preprint on Potapov's result. So I'm going to first give you a very brief, very quick description of what the talk is going to be. So it's basically a description of the abstract, and then we will go into the details. So 6 questions that emerged from the Berling-Lax-Helmholtz theorem. This is the theorem that characterizes the shift invariant subspaces of vector value Hardy spaces. And the first question has to do with having a set F in H2E, a Hardy space with operator value symbols on a Hilbert space E. And we know that EF star, the smallest backward shift invariant subspace containing F, is going to be of the form H of delta. And then the question is, what is the smallest number of vectors in some sense? What is the cardinality in some sense of F that satisfy this equation? And more generally, if a set F satisfies this equation, how can you describe F in terms of delta? To examine question 1, we are led to discuss the functions in F as column vectors of some matrix. This is leads naturally into a strong L2 functions in the sense of Vladimir Pelar, and we will find a new canonical decomposition of operator value strong L2 functions. So question 2 says whether every strong L2 function can be written in the form delta A star. And there is a precursor for that from this, which is the Douglas-Shapiro-Shields factorization for matrix functions of bounded type. Now we're going to see that not all the strong L2 functions are of this form. There is a perturbation, an error that appears. So this has to be, we need to add a plus B here for an exact description. Question 3 is every shift invariant subspace the kernel of a possibly unbounded Hankel operator? And this leads to a new notion of Berling degree for an inner function. And then whether the Berling degree is connected to the spectral multiplicity of the shift operator restricted to the model space, the adjoint of the shift operator restricted to the model space. Then we consider meromorphic continuations of bounded type for operator value functions and use this notion to study spectral multiplicity. And in particular, we ask whether if T is this restriction of SE to the star to A to the model space, for which inner functions does it follow that T is multiplicity free? And finally, the extension of the celebrated Potapov's theorem that says that for matrix functions, in n by n matrix function is rational and inner if and only if it can be represented as a finite Blaschke-Potapov product. So our question would be, what is the analog of this for operator value functions? So we will prove that if
delta is a left inner divisor of the coordinate function, then delta is a Blaschke-Potapov factor, and this requires a new notion of operator value of rational function in the infinite multiplicity case. So most of the time we will remain in the infinite multiplicity case, but for motivation, we will consider sometimes matrix value symbols. So here is an overview of the different sections. So we'll talk about functions of bounded type, Abrahams's theorem for block-Teplis operator, canonical decomposition of strong L2 functions, meromorphic pseudo-continuation, Berlin degree, spectral multiplicity, and the extension of Potapov's theorem. So we start with the unit circle, the open unit disk. Very little new. This audience knows everything about this. So we'll just go very quickly. We have a Teplis operator, we have the Hankel operator. The comment here will be that we want the Hankel operator to go from H2 to H2. So we introduce this unitary that does the trick, right? To bring it back into H2. And we say that a Teplis operator is analytic if a symbol is in H infinity. Now comes the notion of bounded type or Nevalina class for a symbol, which is when you can write phi as C1 over C2, where C1 and C2 are both in H infinity. Helmholtz problem 5 from the 10 problems in Hilbert's space article ask whether every subnormal Teplis operator is either normal or analytic. Recall that normal means that the operator commutes with the adjoint, and subnormal that it is a restriction of a normal operator to an invariant subspace. Cohen and Long in 1984 said no, and they actually gave a concrete example. Abrahamsy in 1976 says yes, but you need to assume that phi or phi conjugate is of bounded type. He actually proved a stronger result if T phi is hyponormal and the kernel of the self-commutator is invariant for T phi, then T phi is normal or analytic. And this is a stronger result in the sense that if I have T phi subnormal, it is hyponormal, and also the kernel of the self-commutator is always invariant. It's actually true, this is even for two hyponormal operators. So the answer to Helmholtz problem 5 is affirmative when phi is of bounded type. Okay. Now, as we know, Berling's theorem states that the invariant subspaces for the shift are of the form theta times H2, and then this leads to the inner-outer factorization for a function, right? You take the function f and write it as theta times g, where g is going to be the outer factor. And Berling also proved that an H2 function is outer if and only if there is an average value formula for the log of g of theta. So the log of the absolute value is 1 over 2 pi integral 0 to pi of the log of the absolute value over the circle with arc length. Given a bounded operator on a Hilbert space, we always know that a closed subspace is invariant under T star if and only if the orthogonal complement is invariant under T. And so that's how we give rise to the model space, which is discussed as defined as the complement, orthogonal complement of theta of H2. Now, this observation falls short of determining which F's in H2 can be cyclic vectors for S star. And for this, something deeper is needed. It's a result of Douglas, Shapiro, Shields in 1970, where they say that a function in H2 is non-cyclic for S star, if and only if there exists a G in H2 and an inner function theta, so that I can write f of z as theta times G conjugate times Z bar, okay? And this is equivalent to requiring that f has a meromorphic pseudo-continuation of bounded type to the exterior of the unit disk. So here is how meromorphic pseudo-continuations come into the picture, because they are associated with non-cyclicity of vectors. And actually, the Douglas-Shapiro-Shields result gives what I will call a certificate of non-cyclicity. Anytime that I have a vector f with the property that S star to the n, f, if I look at the orbit under S star and I look at the closely linear span, take the orthogonal complement, I get theta H2. And theta and G are co-prime, so that means that they do not have any common non-trivial factor. Okay, so theta and G have to be co-prime, and then you get the certificate of non-cyclicity. So what about block Teplis operators? Well, all you have to do here is tensor L2 with C to the n copies of the complex space, and then you define the L2 space, the H2 space, H infinity, L infinity, and so forth. Definitions of the Teplis operators, which are now called block Teplis operators, are natural ones. You need a new version of the J map, a JN map, which will involve the identity matrix for the coordinates. And then as a simple example, notice that if you were to take a symbol like Z bar cube of F, and if I have my function represented as a power series like this, with the F's now being vectors, right? The way the Hankel operator works is that it kind of focuses on F2, F1, and F0. All of these are the powers lower than C cube, and then redefines the function in this form: F2 plus ZF1 plus Z squared F0. Okay, so a block Teplis operator will be made up of regular Teplis operators, classical Teplis operators, as in n by n matrix, and the same for the Hankel operator, and the same for the symbol. The symbol will now be a matrix. We're going to have a notation for the function that takes C into Z bar, phi of Z bar, and then the adjoint as a matrix, and that's going to be called phi tilde. So phi tilde is this matrix that is naturally associated with the symbol phi. So given a matrix value function delta, we will say that is inner if delta star delta is equal to the identity. Notice that we will always put the star on the left, okay, as in the Agler's hereditary functional calculus. And then there are several identities that hold the expected identities, nothing hard here, but we're going to focus on one that is very particularly interesting, that the Hankel operator H phi star intertwines TZ and TC star, and that means that as a consequence, the kernel of a Hankel operator is invariant under the shift operator TZ. So we're going to say that phi matrix is of bounded type if each entry is of bounded type. This, unfortunately, this will not be something that holds when you go to operator valued, but it does hold for matrices. Okay, and then we're going to say that phi is rational if each entry is a rational function. So if delta is inner, it is possible for delta star to fail to be of bounded type. So here is an example: take an H, which is not of bounded type, form an F of this manner. The 3 and the 2 are selected on purpose. And so what we now have is H1 of Z as 1 minus absolute value of FC squared, square root, and form, we verify that H1 is bounded below by 1 over radical 2. And so we also can get an outer function of the same modulus, right? And so with that, the G, now I'm going to manufacture a FG. This is a column vector, which happens to be inner, because when I multiply by delta star on the left, I get the identity. The quantities H1 and G were created to make this possible. But so delta is an inner function, but of course is not, delta star is not a bounded type because it has problems with the F there. Okay. So block Teplis operators had been studied by a multitude of authors, and this is just a kind of a list of some of them. I'm only focusing on people who have done block Teplis operators. Of course, if I had to list all the people who have done work on Teplis operators, it will take me several pages, and the entire audience today will be in there, and the entire audience for the whole semester. But I learned about these operators from Professor Douglas, who was my dissertation advisor. And at the time when I was in Stony Brook, he was working on this monograph from the American Mathematical Society. This was the result of CBMS lecture series that he gave. And so I learned a lot from this book. The shift operator is defined as multiplication by Z on the H2 vector valued H2 space. And the Berlin-Lax-Halmos theorem says that a non-zero subspace is invariant for S if and only if is the analog of Berlin's theorem, but where the theta now is an inner matrix function. This theta is also unique up to a unitary constant right factor. And as a consequence, whenever the kernel of the Hankel operator is non-zero, it has to be of this particular form. This is by the equation that I highlighted before when we were looking at the generalizations of commutator equations for the Hankel and Teplis operators. So VLH is true if Cn is replaced by separable infinite dimensional Hilbert space, and that was Halmos' contribution to the theorem. So that's what it's called, Berlin-Lax-Halmos. Berlin was the scalar case, Lax the matrix value, Halmos the operator value. Now, Gu, Hendricks, and Rutherford in 2006 studied these symbols and proved that bounded type is equivalent to having the kernel of the Hankel operator given by an inner matrix function theta, and is equivalent to having the factorization phi equal A times theta star, where A and theta are right coprime. And I remind you that right coprime means that they don't have a common non-trivial right factor. Here, when we're looking at matrices, we're going to have to start discussing left and right in terms of factorizations. So a question that came to us was, is Abraham's theorem valid for Teplis operator with matrix value symbols? And a simple example shows that without additional assumption, this is not going to be true. Look at, for example, this symbol. It has a self-adjoint symbol here on the 1-1 entry, and it has the symbol of a subnormal operator. So it is the sum of a normal and an analytic, right? So it is subnormal, but it is neither normal or analytic. Part of that is normal and part of that is analytic, but as a symbol, this is not either. So that's not the proper generalization. There has to be something else. So in 2014, with the help of Donggo Kang, also from the Republic of Korea, student of William Lee, we proved a matrix value version of Abraham's theorem in the rational symbol case. And later on, we extended the result to the case of bounded type symbols and obtained what we call the full-fledged matrix value version of Abraham's theorem. But we need this definition of matrix singularity that has to do with the kernel of the Hankel operator. So the kernel of the Hankel operator contained in theta H2, but where theta is a non-constant inner function, that is going to be the test for matrix singularity. And under that assumption, we get exactly what Abraham's has. Hyponormal, the kernel of the self-commutator invariant under T phi, then T phi is normal. In particular, if T phi is subnormal, then T phi is normal or analytic. Okay. Now, the reason I bring this result here is because matrix singularity makes contact with the relevance of having the kernel of the Hankel operator as embedded in its invariant subspace for the shift. So we're going to revisit Berlin-Lax-Halmos and observe that a strong L2 function in the sense of Vladimir Peller is a BDE. D and E will be separable Hilbert spaces. B of the E are the bounded operators from D to E, and defined almost everywhere on the circle with the property, and here is what it is called a strong operator topology idea. For every vector X in D, we're going to have phi of X in L2E, right? So this is Professor Peller's idea that you're going to have a function that for every vector in the domain, you're going to have an L2 function in E. So strong L2 functions have been considered by Nikolsky and Peller. In particular, Peller shows that the set of L2, the set of strong L2 functions constitute a nice collection of what he calls vectorial Hankel operators. And the set H2S has the obvious definition. So we're going to take a strong L2 function, and we're going to look at the kernel of the flip. The flip of phi is the function that changes z by z conjugate. So flip of z is phi of z conjugate. And E prime is always going to be a subspace of E. And delta is an inner function with values in B of E prime and E. So whenever we talk about E prime E, think of E prime as a subspace of E. It could be finite dimensional. Sometimes E prime is finite dimensional. The Hankel operator may be unbounded. Okay, so this is a lemma that whenever you start with a strong L2 function, then the kernel of the Hankel operator associated with the flip of phi is going to be an inner function times H2 E prime, where E prime is a subspace of E. So we denote the orthogonal complement of that by H of delta, and this is now the model space or the Lagrange-Rovniak space. Here's an observation. If E is an operator value function, the kernel of the Hankel operator is shift invariant. We know this. By the BLH theorem, it has to be of the form delta H to E prime. However, delta is not necessarily a two-sided inner function. In fact, if it is, then phi has to be of the form delta A star, where A is an operator value H infinity function and delta and A are right co-prime. This is actually encapsulated by the so-called Douglas-Shapiro-Shields factorization. Later on, we'll see a version of this result for operator valued H infinity functions. Now, as a lemma, let's recall that equation 2 characterizes the class of operator value L2 functions whose flips are of bounded type, where, again, the flip is as denoted here. Now, using this lemma, we can prove the canonical decomposition of strong L2 functions that says that if phi is one of such functions, then you can write it as delta A star plus B. And this is the residue or the remainder that I mentioned in the introduction that you're going to need. So without the B, you have a Douglas-Shapiro-Shields factorization. With the B, you have the decomposition of strong L2 functions on the infinite multiplicity case. So delta is an inner function. Delta and A are right co-prime. Delta star B equals 0. Very important. If I hit this with a delta star, I'm going to hit delta star delta, which is the identity. And so I need to have delta star B equals 0. This B has to be in the kernel of multiplication by delta star. And then the degree of non-cyclicity introduced by Bazunian and Nikolsky enters into the picture here, which is it has to be dominated by the dimension of E prime, where phi plus is the set of column vectors of the analytic part of phi. So I'm going to take phi, I'm going to look at the analytic part, and I'm going to form that as a set of column vectors. All of those will be L2 functions because we are talking about strong L2 functions. And that is going to have a degree of non-cyclicity dominated by the dimension of E prime. And the last condition is that if the dimension of E prime is finite, then this decomposition is unique up to a unitary constant right factor. So in general, there will be very many decompositions like this for a certain phi, but when the dimension of E prime is finite, there will be only one. Now, if phi is in H2S and dk is an orthonormal basis for D, for the domain here, then you can certainly take phi times that dk and form phi k. And so this will now be the columns. And so what you're basically doing is writing the phi as a bunch of columns like this. Each one is an element of H2. And these are scalars. This is an honest to goodness matrix, infinite matrix, whose columns are elements of H2. So this is one way to visualize what's going to happen with this phi. If in addition we know that phi has the factorization, right, then delta star phi will have to be A star, and therefore phi will be written as delta delta star phi plus B, with V in the kernel of delta star. So here's another way in which we'll be able to write this, perhaps a more revealing way, because now you have the phi of both sides. Phi solves this type of equation, right? All right, so now recall that a strong L2 function has the property that the kernel is given by an invariant subspace of H2, and that the Hankel operator may be unbound, okay? So we will say that the inner function is the complementary factor of the inner function delta C is a complementary factor of the inner function delta, if when I take delta C as a row matrix and multiply by the column delta star C, I get the identity. Each of these functions is individually an inner function. So if I multiply, if I put the star on the left on delta, I get 1. If I multiply by the star on delta C, I get 1. But the idea here for complementary factor is to go the other way around and allow delta C to fill the gap. Delta star in general is not equal to 1, it's less than 1. So you fill the gap with another positive piece. So if phi is an n by n matrix, then the following are equivalent. Phi is of bounded type, in the sense of each component is we're looking at matrices here. So each component is a bounded type. It's never linear class, quotient as 2H infinity functions. Or the kernel of HV star is equal to delta H2 Cn for some two-sided inner matrix function delta. So as a corollary, we have that when delta is inner, the following are equivalent. Delta star is a bounded type, delta flip is a bounded type, or the delta C is a two-sided inner. And two-sided inner, if you do the multiplication here, you will see that it means that delta star delta C is equal to 0, or in other words, the range of delta and the range of delta C are perpendicular. So this is reminiscent of the equations that one sees in the Kunz algebra, right? So recall question 1. If I have a set F containing H2E, and I look at EF star as the smallest backward shifting invariant subspace containing F, there exists a delta so that H delta is EF star. And the question was, can you tell me what's the smallest number of vectors is in F satisfy this equation? Or more generally, describe for me F in terms of delta. So here is an answer to question 1. I look at a phi, which is a strong L2 function. I denote by phi plus the set of column vectors of the analytic part of phi, and the following are equivalent. Phi flip is of bounded type. The set E phi plus star, so when I take phi of this form, right, when I take F of this form as the columns of the analytic part of a phi, which is in a strong L2 function, is going to be H of delta for some two-sided inner function delta. Then the phi plus as a collection of vectors will be contained in the model space for some two-sided inner function theta. And finally, if I take any sub-collection phi k1, phi k2, and so forth contained in this phi, right? These are all the columns, but I'm taking some sub-collection, and I form this psi, capital psi, then as a matrix, then I will have the flip of that of bounded type. So this allows me to also check that if I take just a sub-collection and I form the matrix and I get the flip to be of bounded type, then the whole phi tilde, phi flip will be bounded type. I think LaTeX called this brev as opposed to flip. The flip, I think, is more descriptive of what it can. Okay, so here is a result from Pellar's book. If phi is a strong L2 function, then H phi, the Hankel operator associated with phi, can be extended to a bounded operator on H2 of the, if and only if there exists a function xi in L infinity such that xi hat, these are the Fourier coefficients of xi, coincide with the Fourier coefficients of phi for n negative, and also the norm of the Hankel operator is equal to the distance from C to H infinity. Okay, so this gives a characterization of when the H phi, which a priori is an unbounded operator, can be extended to a bounded operator. So this is related to question 3. Is every shift invariant subspace the kernel of a possibly unbounded Hankel operator? And here is an answer. If delta is an inner function with values in B, E prime E, then there exists a function phi, strong L2 function, with either D equal E prime or D equal 1 dimension more than E prime. So C plus E prime, satisfying that the kernel is delta H2 prime. So you start with an inner function with values on bounded operators on E prime to E prime subspace of E. Then there exists a function phi, strong L2 function, where the domain D here is either E prime or E prime plus 1 more dimension, and then satisfying that the kernel is equal to that. So the answer is yes, modulo that adjustment in the domains. So we're going to now switch to meromorphic pseudo-continuations of bounded type, just to show you a connection to that result of Douglas, Shields, and Shapiro. So we are going to say that a function with operator value function C psi is said to be meromorphic of bounded type if it can be written as G over theta, where G is a strong H2 function in the exterior of the unit disk, and theta is a scalar inner function in the exterior of the unit disk. So a function phi is said to have a meromorphic pseudo-continuation of bounded type if phi hat is meromorphic of bounded type in the exterior, and phi is the non-tangential strong operator topology limit of phi hat. So here you need this condition that for functions that are defined on the exterior of the open unit disk, you want to have non-tangential strong operator topology limits. And so this is the condition that you need for meromorphic pseudo-continuation. So D and E separable complex Hilbert spaces, orthonormal basis D, J, and EI. So you can form a meromorphic pseudo-continuation of bounded type, and then form the coordinates of that meromorphic pseudo-continuation. So if you do the D, J, EI, this is a bounded type. So the connection with meromorphic pseudo-continuation is that when you have it, you need to have bounded type for each of the coordinates. These are functions now, regular functions in L infinity. So for phi, described as a matrix, as I mentioned before, this is the matrix of the columns of phi, which are strong. Phi is a strong L2 function, so all the columns and L2 functions. We're looking at a matrix here. The following are equivalent. Meromorphic pseudo-continuation is equivalent to bounded type, is equivalent to bounded type for each of the coordinates. We're talking about bounded type of the flip, of course. And now we're going to now make a connection with spectral multiplicity, and this will come in the form of a so-called Berling degree, which is defined as follows. This takes a little bit of parsing, so bear with me. So we start with a phi. We start with the delta. Delta is our inner function, and we look at phis that can be written as delta A star plus B, as in the canonical factorization, canonical decomposition of strong L2 functions, right? This is the generalization of Douglas-Shapiro-Shields factorization. So I write the phi like this, and then I inspect the domain D, and it has a dimension, is either an integer, positive integer, or infinity, and we look at the infimum of that. So the infimum of the dimensions of the Ds for which there exists a pair AB, such that the symbol phi can be written as delta. Delta is the delta coming from the inner function. Delta A star plus B, and is the in the canonical decomposition. So that's the definition of the Berlin degree for an inner function. And now we're going to see what's the connection with that, with the so-called spectral multiplicity. So spectral multiplicity, on the other hand, this is very traditional, 1940s or 1950s. Take a linear operator T acting in a separable complex Hilbert space, look at the infimum of the dimensions of F, where F is contained in E, and the infimum is taken over all generating subspaces. So I'm going to look at all subspaces F, take T to the n of F, right? And then take the closed linear span, and it has to be E. So that's a generating subspace. Once I have one of those generating subspaces, I calculate the dimension, and I do this for all of the generating subspaces. I take the infimum, that's the spectral multiplicity. So here is the answers to questions 4 and 5. These were the questions where they're saying, what is the connection between Berlin degree and spectral multiplicity? And for dimension E prime less than infinity, and if we take the operator T, as what we should be doing is that the adjoint of the multiplication operator by the coordinate function restricted to the model space, then mu T, spectral multiplicity in the sense of the mid 20th century, is equal to the Berlin degree of the inner function as defined before in terms of the decomposition, the generalization of the Douglas-Shapiro-Shields decomposition. Here's a corollary. When the rank of I minus T star T is finite, so when the defect operator has finite rank, then the multiplicity is also equal to the Berlin degree. So I have saved the last few minutes for the extension of Potapov's theorem, and we're going to start recalling what a Blaschke factor is and what a Blaschke-Potapov factor is, which is you look at this V alpha, you multiply times a projection onto subspace, and then looking at the orthogonal projection onto the complement. So it's a convex combination of the Blaschke factor and 1 using PM as the foundation. So you look at projection over M and projection onto the orthogonal complement of M, but in one of them you put a Blaschke factor, in the other one you don't put anything, you just keep the projection as is. So a function is called an operator value finite Blaschke-Potapov product when it's a product of these guys. So here you're going to have a finite number of projections, different Blaschke factors, and then you take the multiplication of all of that times V, a unitary, and that is D, which is a product. Okay, so D is a function here. In particular, a scalar value of function D reduces to a finite Blaschke product because you're going to have a unit modular scalar in front, and then the product of Blaschke factors. Potapov in 1955 proved a remarkable theorem that an n by n matrix function is rational and inner if and only if it can be represented as a finite Blaschke-Potapov product. Okay, so rational and inner. We're going to try to generalize this result. What is the extension of this result to the case of operator value functions? So this leads to a natural question. What is the left inner divisor of the coordinate function? I call this the coordinate function is multiplication of Z times the identity matrix. What are the left inner divisors? We may initially guess that each left inner divisor is a Blaschke-Potapov factor. More specifically, with Insum and William, we thought for a moment that if a left inner divisor of these Z00Z should be of the following form up to a unitary constant right factor, also up to unitary equivalence. So are these the only possibilities? 1001, 100Z, Z001, and Z00Z. And for example, look at this A, and this is a left inner divisor of Z00Z, Z, because if you do this multiplication, you can see how by taking a unitary of this form, 1 over radical 2, 1, 1 minus 1, 1, you can show that is a left inner divisor. So it's a simple calculation. So in 2012, we proved that every left inner divisor of the coordinate function is a Blaschke-Potapov factor. Okay, and so this leads to consideration of left inner divisors in the infinite multiplicity case. And incidentally, this fact is useful to study coprimeness of functions. So the question is there, is this still true for operator value functions? When the dimension of E is finite and theta is H infinity of B of E, now this is E now is finite dimensional, it's a two-sided inner function. Any left inner divisor is a two-sided inner. That's something that is contained in the memoirs from 2019. But we can say more. We can actually say that if theta is an H infinity of BE as a two-sided inner function, and if delta is in H infinity of BE, is a left inner divisor of theta, then delta has to be two-sided inner. So in particular, when theta is of the form scalar theta times the identity of the space E, every left inner divisor of theta is also an inner divisor, so two-sided inner divisor of capital theta. However, in general, left inner divisors of a two-sided inner function need not be a right inner divisor. So there is a lemma that we prove that says that delta is an inner divisor if and only if delta is an inner divisor if and only if theta delta star has to be in H infinity. And here is an example that will help you visualize how this works. You take a delta, which is defined as, it's like a weighted shift in some sense. You look at En goes to En plus 1 times Z when n is bigger or equal to 0, and goes to En plus 1 for n less than 0. So the only difference between negative and positive integers is that for negative ones, you just shift a vector, E minus 2 goes to E minus 1, say. And for positive integers, you multiply by Z. So E3 goes to E4 times Z. Now, theta does something different. It takes an En and sends it to E to the sub minus n plus 1 minus n. So you kind of have to flip the n. And then for n bigger than 1 and for n less than or equal to 1, you multiply by Z squared. Both of these are two-sided inner. You can check it. Two-sided inner. Now, delta star En is given by this, is the adjoint of that one. And when you do delta star times theta, look what you have. You got three categories. If n is less than 1, you get something with Z. With n is equal to 1, you get a Z squared. And when n is bigger than 1, you just get 1. Thus, delta is a left inner divisor of theta. However, if you do the multiplication the other way around, theta times delta star, you don't get what you were hoping for. So this is not a right inner divisor of theta. Here's another example. Now we take S to be a shift operator on H2, defined in this way, and let delta of Z to be that particular S, right? Is an inner function. So delta star delta is S star S equal to the identity, which implies that delta is a right inner divisor of the two-sided inner function identity, right? It's a right inner divisor, it's right there, right? However, this is not two-sided inner because we know that the shift is not unitary, right? So delta is not a left inner divisor. So we're going to define a function to be rational when for some finite Blaschke product theta, the multiplication theta times H2 falls inside the kernel of the Hankel operator associated with phi star. Okay, so this is the definition of rational, which agrees with the standard definition in the case of one dimensionality. And our theory means that if you take a theta, a finite Blaschke product, and if delta is an inner divisor of capital theta, which is that little theta times the identity on E, then delta is a finite Blaschke Potapov product. And if we recall that phi is a null infinity of E, the kernel is of this form for some delta inner, and the Douglas-Shapiro-Shields result, we can now consider the case of phi. So this is just to put this corollary into context. The function is rational if and only if phi is of the form delta A star, right? That's what they have proved there, where delta is a finite Blaschke Potapov product, and A is such that delta and A are right coprime. Okay, so that's what that we can prove for the case of extension of the Potapov result. And so the answer to the question 6, which is the extension, operator valued extension of Potapov's theorem, comes naturally as a two-sided inner function phi in H infinity is rational if and only if it can be represented as a finite Blaschke Potapov product. Now, these require a new definition of rational, which we didn't have for the case of operator valued symbols. And also we had to adjust the situation concerning metamorphic extensions to the exterior of the unit disk. Thank you very much for listening.
Thank you very much. We have time for questions. So if you have a question, then please just go ahead and.
I'm checking the chat.
If there aren't any questions, then let's thank our speaker again.
Thank you.
And we will continue in 13 minutes.
Okay, thank you.